The Raspberry Pi is a great device, but in some applications it could use a bit more processing power. So let's see if we can squeeze a bit more speed out of it using overclocking. Hi and welcome to Bytes and Bits. By default, the Raspberry Pi, the processor speed is set to a nice safe operating speed. That doesn't cause any problems with regards to stability and heating. But without too much problem, we can actually push that a little bit faster to get some extra performance out of it. So in this tutorial I'm going to have a look at how we can do that for all Pi models, but specifically then for a Raspberry Pi Zero, which of course is one of the least powerful versions. And in my handheld retro games console project, obviously we need as much power as possible from this little device to make sure that our games run as smoothly as possible. So let's see just how easy it is to overclock your Raspberry Pi. Before we start overclocking our Raspberry Pi, just one little word of caution. Obviously, with overclocking the Raspberry Pi, we are pushing it outside of its normal operating conditions, and this may lead to some permanent damage on your device. Now, the Raspberry Pi is very well protected, so that is highly unlikely, but just do be aware that if you really do push it really hard and the system overheats by too much, then obviously we can destroy some of the components actually on the circuit board. Some of the overclocking settings that we do use will actually blow a little security fuse inside the device itself, and that is something which actually indicates that the system has been overclocked and obviously pushed outside of its limits. So do bear in mind that that does invalidate your warranty, and obviously if you're going to sell this on to somebody else, they may well be able to check that and see that you have been messing about with it. So do be aware of the implications of overclocking your Raspberry Pi. But as I say, the chances are that it's very unlikely that you will damage it. The worst that will happen is that it will crash and you will have to then reboot your system. So let's start by thinking about what overclocking actually is. Well, all microprocessor systems rely on clock signals to control the way they work. And these clock signals are simply voltages that repeatedly flip from 0 volts to some supply voltage, and perhaps 3.3 volts, or whatever the microprocessor works from. And these microprocessors, they turn your program commands into a series of electronic steps. And the processor takes a step each time it receives a pulse from its clock signal. So the basic principle that we're doing in overclocking is that the faster we send these clock signals, the faster the processor will work through these steps, and therefore the faster that your program will run. So in essence, overclocking is a fairly simple idea, but of course there are a few issues that we're going to run into. If we look at the timing diagram, we'll see that the clock pulse, which is the top one here, when we go from our low to our high and our high to a low, we don't have what's known as a perfect square wave. The transition line isn't vertical, it actually is a slope, and this is called the slew rate of the signal. In other words, how fast it can change between one state and the other. And the problem then is as we get faster and faster clock rates, this slew rate doesn't change. So the slope of that line doesn't change, but we are then decreasing the length of time in between our changes. And eventually, the length of time between our clock pulse getting to a state and then changing out of that state becomes too low. We need a certain stable time for the processor to be actually able to do anything during that clock pulse. So if we go too fast and our slew rate limits our stable time, then our processor will just simply not be able to do what it needs to do and it will crash. And of course, this operation isn't just happening on the clock signal, but all of the internal bits which are flipping inside the processor itself. So we need to be able to, as we get faster and faster, we need to increase the slew rate so we get a more vertical line. And we do that by increasing the processor voltage, and we have what's known as overvoltage. Now, of course, the problem we have is as we increase frequency and as we increase voltage, we increase the power dissipation inside our processor, and that power is dissipated as heat, so our processor gets hotter and hotter and hotter. So we need to find a situation where we can balance both the clock speed rate, the over voltage to get the slew rate going as fast as possible, and the heat dissipation in the processor, so we get a fast processor which runs stably at a cool temperature. So with this extra heat being generated on our board, we can of course add some extra cooling, either with a simple passive heatsink, which is basically a piece of metal which we stick onto both our processor and, if we want, our RAM chip using some thermal paste, or we can of course use active cooling where we add an actual fan to that as well. Now, depending on how hard we overclock our processor, we may or may not need this extra cooling. And for my particular use case, where I'm building a little handheld games device, I don't really want to have to add in this extra cooling, especially not one with a fan, because of course that will put extra drain on my battery. So I'm going to be aiming for no cooling, so my Raspberry Pi running cool enough without any extra. If I then at a later date want to add an extra little heatsink on there, and perhaps once I put it inside a case that situation may get worse, at least I have a little bit of leeway where hopefully then that extra passive heatsink will help me out. So now that we know a bit more about overclocking itself, let's work out how we can actually apply it then to our Raspberry Pi. It's very simple actually with the Raspberry Pi. We just simply have to add a number of overclocking parameters into our /boot/config.txt file. And if you've been following through this games console project, you'll have seen us add other parameters in there. And this is a file which basically, when the Raspberry Pi boots up, it reads the bits of information from this, and that helps us set up some of the hardware. Now, if you go to the main Raspberry Pi documentation page for this overclocking, again, I'll put links to that on the project page in my main website, so please do have a look in the description down below for a link to that. There are the whole set of parameters listed out that we can have a play with. But the main ones that we want to have a look at are our ARM frequency, and that then controls the frequency of the actual processor CPU, the main ARM processor inside our system on a chip. We want to have a look at this GPU frequency, which is sort of like a block setting for a number of different parts of our graphics system. We then have our core frequency, which allows us to separately set the core processor in our graphic processor. We'll also want to have a play with our RAM frequency, so this SD RAM frequency. As we've seen already, we then need to start applying some overvoltages. So we have a general overvoltage which will increase the voltage on both our CPU and our GPU cores, and then an overvoltage SD RAM, which will of course just raise the voltage slightly on our SD RAM chip. If we scroll a bit further down on this page, we'll come to a useful table, which gives us the default settings for each of these values. So you can see here that we have all the different types of Raspberry Pis listed out with these particular settings. Now for us on the Raspberry Pi Zero, you'll see here that we have our ARM frequency. We then have this block of frequencies here, which are the GPU frequencies. Now remember, we had a single GPU frequency setting which actually sets all of these values here together, and then we were able to use core frequency to just adjust the individual frequency of the actual GPU core processor. So we're now ready to actually start setting these parameters and seeing if we can improve the performance. But we need some sort of way of measuring this improvement. So let's first of all look at our standard system, and we'll see if we can get some measurements for the processing power of that. And to do that, we're going to use a little package called Sysbench. So if you haven't already installed that, you'll need to use your sudo apt-get install Sysbench. And once that's installed, we can then run a number of tests. And these tests are also soak tests where we'll actually be stressing our components so that if we are going to get a temperature rise, we will see that. And then we'll measure how long it takes to do a specific task. And then obviously once we have added some of our overclocking parameters, we'll then reboot the system and then repeat the tests and make sure our temperatures are okay and then see if we've actually improved the speed. To start then, we'll just check the current state of the system. So we'll first of all have a look at the current processor speed using this command, and we can see there we're running at 1 GHz. We can then check the current temperature of the system, and we can see we're there running at 60.5 degrees centigrade. Again, all of these commands, you'll find them on the project page in my main website. The first test we'll run then is for the CPU. And this test simply gets it to check all the numbers up to a certain limit to see if they are prime numbers. And again, you can adjust that with the CPU Max Prime option at the end there. So 2000 on my Raspberry Pi takes about a minute, which is a reasonable amount of time to wait. And once that's finished running, we can then check our temperature just to see if there has been a rise. So from this we can see that we're taking 54.6 seconds to run the test, and we're getting around about a 2 degrees centigrade rise in temperature. So next we will do a memory test. So this command will do our memory test, and really what the parameters are specifying is the block size tells us how big an area of memory we're going to use to read and write to. And then the total memory size, that tells us how much total amount of RAM we need to write to finish this test. So in effect, if we're choosing a 1 megabyte block of RAM, we're going to have to write to that 10,000 times to get our 10 gigabytes worth of processing. And again, you can see there, this takes about 24 seconds to run, which is a nice amount of time. To test our graphics processor, if you're running a desktop, there are obviously benchmarking tests you can run there, which will display things on the screen. But for me running RetroPie, the real test is to run actual games and see what frame rate we get. So I'm using a Super NES emulator for my Raspberry Pi Zero, and there's a couple of games which will stress that quite well. This first one here is Doom, and you can see we're getting a pretty low frame rate in sort of 18 to 20 frames per second. If we then try it in Donkey Kong Country, which again stresses the processor, you can see we're getting a better frame rate, but it's still not running at full speed, and we're hitting around about our 40 frames per second. And ultimately, it's this frame rate and game performance which is what I'm trying to optimize for. So that gives us a set of results for our default settings. And obviously it's good to run them a few times, especially our processor memory tests, to average out our readings. And again, I've run each one 3 times here. As you can see, the general results are very similar. So that gives us a good indication that this is the true speed that we're seeing. So now we've got some data about our default performance. Let's start adding in some overclocking. So we're going to have to edit our /boot/config.txt file. Now inside there, if you come down, you will probably find a little section where it talks about altering the ARM frequency. So you can add some stuff in there, but I'm just going to create a new little section which is my overclocking section. And inside there we can start to add in our parameters. So the first one we're going to look at is our ARM frequency, and it's best when you're doing this to do them one parameter at a time. As we go higher and higher in our overclocking, we will start to crash our system. So if we're playing with all 3 at once, it'll be hard to work out which was the one that we've pushed too far. So just to take one at a time, take it up as high as you can, and once you've got that working stably, move on to the next. So let's start looking at our ARM frequency. So if I come in here and do this, I'm going to first of all show you what happens when we go too far. So obviously our default ARM frequency is the 1000 megahertz. If I'm going to push it up to 1500 megahertz, which is 1.5 gigahertz, that should not work. So let's try that to begin with, and we'll show you how to get out of the situation where you have crashed it and it isn't able to start. So I'm going to do Control X to come out of here, then a yes, I'm going to save that, and save that, and then I'm going to do a sudo reboot now. As the system reboots, it does take a bit of time before it actually gets to setting our overclocking parameters, so initially it will look like everything is going okay. But eventually it will get to a point where it is hanging, and at this point my system is now stuck on this screen, and if I try and access through SSH it just can't be reached, so the system has now crashed. We now of course need a way of getting back our system even though we can't boot it up. I found the simplest way is to take the SD card out of the Raspberry Pi and plug it into my main computer. It will come up as 2 disk drives, and we want the boot drive, which matches of course in with the boot folder on our Raspberry Pi. Inside that you'll then find your config.txt file, and you can simply open that up with Notepad or a similar text editor, re-edit the file, save that, and then put it back inside your Raspberry Pi. And once you've done that, you should find that the system then is able to reboot and we're back to working with our normal system. So it's really a matter now of trying to work out what are the best settings for your particular board. And again, you can find some starting points on various websites. So I'm at a tomshardware.com page here, and that does list out various overclocking settings that they've used for each different Pi model. So again, I'm using a Raspberry Pi Zero, and you can see here that they were getting up to 1.1 gigahertz on their ARM frequency, and so on, and again using some overvoltage here. So that shows you where you should be aiming towards. Now you will find that different Raspberry Pi Zero boards or any other boards, they do differ between actual boards themselves. There's a lot of randomness that can happen when the components are manufactured. So they will all work at the safe stated operating range, but you will find that some just happen to have been made just slightly better than others, and they will be able to run faster. So you do have to do a bit of playing about just to find what works best with your particular board. But these figures posted here are ones which will generally work with pretty much any board out there. So I'll take you through just how I just do the fine-tuning bit on my board. So really we're editing our config.txt file and adjusting the particular frequency that we are playing with. So I'm incrementing this in small increments, and again we just keep doing that. We then reboot our system and then see if it works or not. So eventually, after a few edits, we'll get to a position where we make a change in our frequency. We will then save that and reboot our system. Sometimes everything seems to be working correctly, but as soon as we try to use it, the system crashes. So we know that this frequency is close to working, so we can try editing our config.txt file and adding in some overvoltage to just help those slew rates and see if we can get this to work. Again, we need to save that and then reboot our Raspberry Pi and see what happens. And again, it may well seem to boot up, but it's not until we actually get into the Raspberry Pi and start doing some stress testing on this particular aspect. So this one here is the processor. If that all then works fine, we can try it a couple of times, then we know that we have a stable system. And of course, we'll want to check both our temperatures and just check that our processor is running at the speed we've set it at. And from here we can then go back and increase that ARM frequency again, and if we need to again then add some extra overvoltage. But eventually we'll get to a stage where we've got it going as fast as we can, and as keeping the temperature down to whatever limits we decide to place on it. Remember, There's no real right answer to this. You do have to keep in mind what application you're going to be using this for. So in mine, I may be able to push it faster and faster, but of course that will use more and more power. So I have to get a bit of a trade-off between my final outcome here, which is nice playable gameplay, and of course my battery power. And again, this is entirely up to you as to where you push your Pi to and what temperatures you're happy with and what power consumption. So after a bit of playing about, these are the values which I finally settled on. And as you can see, they're quite a bit higher than the default settings on the standard Raspberry Pi Zero. So if we now rerun our core processor and memory tests, we should find that we get much better performance. And of course, for my handheld game system running in RetroPie, the real target is to get higher frame rates in our games. And you can see here in our Doom, we're picking up a good sort of 4 or 5 frames per second on our overall performance. And then in Donkey Kong Country, well, really we've hit our target of 50 frames per second. Okay, it does dip below a little bit now and again, but in general, we are running at full speed. So looking at the overall statistics then, again with these particular tests, our performance in these, on the processor side, we've improved by about 20%, and on our memory side, probably by about 30 to 40%. And of course we're seeing then some nice increases in our frame rates. So as a final test, we need to make sure that our system is stable for a longer period of time. So we can run the memory and processor tests using larger numbers to make them run for longer periods, or we can obviously then just play our games just to make sure that it's stable inside our final environment. So instead of having to type in our temperature command all the time, we can use a watch. So this says create a watch, so every 2 seconds run this command, and that should now run just sitting there in the background for us. And we can then go and start and play a game. And again, a game which we know is sort of pushing our system to its limits. So if we start up Donkey Kong, we can obviously play this game and see what happens. So we can see that our core temperature is staying fairly stable around about that 60 degrees centigrade mark. There's a little bit of variation, but there's not any general overall trend of it getting hotter and hotter. Obviously we'd need to let this run for an amount of time and try it in different games and different scenarios. But as far as I'm concerned, I feel that I've got a reasonably stable system now. It's giving me good performance, so I'm happy that that's all we need to do as regards overclocking. So hopefully that's shown you how to tweak the performance of your Raspberry Pi using these overclocking parameters in the config.txt file. As you've seen, I've been using this technique to improve my Raspberry Pi Zero's performance for RetroPie, and this is part of my handheld retro games console project. If you want to watch any of the other videos in this series, then please check out the project page on my main website, where you get links to all the other tutorials, along with all the codes and information for this overclocking video. Also, if you haven't subscribed to my channel yet, please do click on the subscribe button, turn on your notifications, and click the like button to let YouTube know that I'm making useful content. So I hope to see you in another video very soon, and bye for now. Don't forget to visit the course pages for this project. There you'll be able to download the code for this lesson and get lots of extra hints and tips. You'll also get access to all my other programming, electronics and gaming projects. All the links are in the description below. For more games programming, electronics projects and retro gaming, please make sure you like this video, subscribe to my YouTube channel and visit my website.